So these intermolecular forces depend on the structure of the particles. Like I said earlier, the state of matter at a particular temperature depends on the strength of the intermolecular forces. If the forces holding the particles together are very strong, then that substance will have a high melting point and a high boiling point. If the forces holding it together are weak, we'll see low melting and boiling points. So what are these intermolecular forces? Where do they come from? They come from interactions between charges, could be ions, partial charges, which could be polar molecules, and temporary charges on particles. So these are the three different types of charges that can cause attraction between molecules or atoms. We've talked about Coulombs Law before. Here it is again. E, the potential energy of two oppositely charged particles, Q1 and Q2, so those are the charges on the particles. One's going to be positive and one's going to be negative for us to have attraction. A negative energy means the energy gets lowered and the things are attracted to each other. So that energy is proportional to the product of the charges divided by the distance between them. So if we increase the distance between the particles, then the attraction between them is less. If we increase the amount of charge on the particles, the attraction is greater. This 1 over pi epsilon is just a constant. And so a lot of times, and I would encourage you to think of Coulombs Law this way. I don't want to do that in red. Blue's nice. The energy is proportional to Q1, Q2 over R. So our force of attraction will be greatest when R is small, when the particles are close together, and it will be greatest when the magnitude of those charges is larger. If you've got a positive 2 and a negative 2 charge, you're going to have a much stronger attraction than if you have a +1 and a -1, or a partial charge, maybe a +1/3 and a -1/3. That makes sense? So bonding forces that we talked about in the previous 2 chapters, those involve large charges at very short distances. Intermolecular forces are a lot weaker because we've got smaller charges at greater distances. So here's a water molecule, and the bond between oxygen and hydrogen, the distance between these two atoms is about 96 picometers. So that's a very short distance. The intermolecular force between one molecule and the next is about 300 picometers. So it's about 3 times the distance of a bond. And the force of attraction is proportional to 1 over the distance. So if the distance is 3 times greater, the force of attraction is 3 times smaller. So what are these forces? The first one we're going to talk about is called the dispersion force. It also has a bunch of other names. It's sometimes called the London force, or a London dispersion force, or a van der Waals force. I'm going to try to stick to dispersion force. It's also called induced dipole forces. Sorry about that, but those are all the names that I can think of. So what is this? This is an intermolecular force that is present in all molecules and atoms. Everything has dispersion forces. And these come about by fluctuations in electron distributions. So if we look at an atom, what atom is this? Can you tell? It's helium. We've got 2 protons, 2 neutrons, that doesn't matter so much, and 2 electrons. So this is helium. So here's a helium atom. And we've talked about what the electrons are doing. They're in these standing waves, right? And so they're occupying these orbitals. For the purposes of talking about intermolecular forces, it's more convenient to think of them as actual particles. So if we were to take a picture of a helium atom, then we would force the electrons to be particles, and they would have to have a location. So we take a picture, there they are. We take another picture, there they are, they've moved. We take another picture. Oh, this time they both happen to be on one side of the nucleus. It's random movements. It can happen. They're both on one side. This is going to cause the charge distribution in the atom to be lopsided. Both electrons on one side means that this side of the atom is going to be a little bit negative, and the other side is going to be a little bit positive. Does that make sense? So this reminds me of a time when I walked into the living room, and all 6 of my children were sitting on half the couch. They were looking at a book or doing something, and I was like, what the heck? I've never seen that before. Usually they're scattered all over the place. Now they're scattered kind of all over the state, right? They grow up and they go away. That's what people tell me, holding on to that thought. I love them, but yeah. So just randomly distributed, okay? So things can get lopsided, and that happens with electrons in atoms. So in any given instant, an atom or a molecule can have this uneven electron distribution. So then what happens? So you get one atom that's spontaneously lopsided. Then this induces a dipole, that's called a dipole, an instantaneous dipole, like a polar bond where you have one side positive and one side negative. But here it's just the atom. That induces a dipole in the next atom because this positive side of this atom attracts the electrons in the neighboring atom. And that causes this to have a dipole as well. And then we get this attraction between this temporary positive charge and the temporary negative charge on these 2 adjacent atoms. This one then induces a dipole in the next one, and then there's attraction there. These dipoles are instantaneous. They're extremely temporary. They only last a short period of time. The kids sitting on the couch lasted, I don't know, maybe a minute. And that was over, and I don't think it's ever happened again. I took a picture. I should find it and put it in the slides, but I don't know where it is because there's too many pictures. This is I think of this a little bit like my husband and I went to San Francisco, part of our honeymoon, and we took one of the blue and white cruises on the San Francisco Bay, which is very, very cool. We did not take the one that goes around Alcatraz, but let's pretend we did. So you've got this boat, right? You imagine a boat with a bunch of people on the deck, out sightseeing, right? And the boat goes around, and it's getting close to Alcatraz. Where are the people going to go? They're going to go to the side of the boat that is closest to Alcatraz because they want to see Alcatraz, right? So all the people go to one side of the boat. Now, hopefully they, haven't overloaded the boat or anything, but you can imagine that the boat might list just a teeny tiny bit if all the people went to one side. So that's an instantaneous dipole, an imbalance. The site of Alcatraz attracted the people. This positive, instantaneous partial positive charge attracts the electrons in the neighboring atom and causes an imbalance in that one. That make sense? So, very brief interaction. The magnitude, how strong that dispersion force is, depends on how easy it is to push around the electrons on a given atom or molecule. A larger electron cloud is easier to polarize because the electrons are farther away from the nucleus. We've talked about, as you go down a group in the periodic table, like the noble gases, helium, neon, argon, krypton, xenon, we see that the molar mass increases, and we also saw that the radius of the atom increased. They got bigger and bigger. And so the electrons in xenon on the outside are much farther away from the nucleus than the outer atom electrons in helium. So they're not held as tightly. They're more loosely held. I think of it as being kind of large and jiggly, right? And so it's easier for those electrons to get lopsided. There's a lot more of them, too. So a larger electron cloud is easier to polarize because they're less tightly held. The more easily it is to polarize those electrons, the stronger the force of attraction caused by that dipole force. And so what we see here is a trend with the noble gases that the boiling point increases as the molar mass increases. The only force of attraction between noble gas atoms is a dispersion force. You'll notice that these boiling points are in Kelvin. So helium boils, turns from a liquid to a gas at 4.2 Kelvin. That's just barely above absolute zero. That's crazy, crazy cold. And even xenon boils at 165 Kelvin, which is way, way below 0 Fahrenheit. But there's a trend here. Okay, so as the atoms get larger, the amount of attraction between them becomes greater. The boiling point is related to the dispersion force strength because how does a liquid become a gas? Well, first of all, why is the liquid a liquid? It's because these intermolecular forces are holding the particles together, right? I might be, no, I'm not getting ahead of myself. I probably am, but it's so far ahead that I don't even know yet. So the liquid molecules are moving, right? And when they begin to move fast enough, they can break away from the attractions with the other atoms and escape into the gas phase. And so this increase in temperature tells me that for xenon atoms to escape, they need a lot more thermal energy than helium atoms need. And that's because the forces of attraction between them are stronger. Sometimes I think about these intermolecular forces as being like Velcro, right? So imagine a group of people wearing Velcro suits, right? And as you're milling about in a confined space, you're sticking to each other, right? And so it's hard to move. You know, if you're not energetic and strong, you're going to get stuck to each other, right? But if you're moving quickly, then you're going to be able, there's resistance, but you're going to be able to get through, right? And to get into the gas state, to break away from all of that, you have to tear yourself away from the Velcro. Have you seen those inflatable bounce house things where there's this big Velcro wall? And you put on a suit, and you bounce, and you bounce, and then you bounce up against the wall, and you stick, right? And you're like, how does that work if I can't even get my Velcro shoes to stay together? It's a lot of Velcro, right? How do you get yourself off of there? You have to peel yourself off, right? It takes energy to break that attraction of the Velcro suit to the Velcro wall. So the size of the atom affects these dispersion forces. The shape also. Now atoms are spherical, but molecules are not always spherical. So let's look at two molecules, N-pentane and neopentane. So the difference here, they both have the same number of carbon and hydrogen atoms, so their molar masses are the same. The difference is how those are connected. So normal pentane, N-pentane is just, ooh, ouch. You should count up all the bruises that we've gotten from the handles on these drawers. I'm not distractible at all. Yeah. So this one's kind of long and skinny, and this one's round. And if you think of this as Velcro, right, something covered with Velcro, when this hits a wall, it's got this big surface area to stick. If you've got more of a sphere, like a ball, only a little part of it can stick. And so this is going to have a higher boiling point than this one because it has more opportunities for interactions. So over here, this is the structural formula for N-pentane, and this is the one for neopentane. And so we see this one's got a tetrahedral shape, and this is just a long line. So here we've got two of these molecules, and they can get interaction along this long side. They can stick together pretty good. These two are more spherical, and so they can only touch at a very small point, and so just a little bit of Velcro touching is not going to work. They're not going to stick together very well. And we see that neopentane has a boiling point of 9.5 degrees Celsius, and pentane 36.1 degrees Celsius. Their molar masses are the same. is the shape of the molecule. So if we're looking at similar elements or compounds, molar mass is useful, but molecular shape also plays a part. Here we've got same molar mass, and so then the shape, we can look at the contribution of shape. Any questions? These are similar molecules. They're hydrocarbons, just carbon and hydrogen, and they all have the carbons in a straight chain. So we're not comparing round, ball-like, globular molecules. We're looking at more linear molecules. So they're all roughly the same shape, but we see as the molar mass increases, the boiling point increases. And this is because the dispersion force increases with the amount of surface area and with the size of the molecule. So this longer one is more easily polarized, and so you can get a stronger dipole going, and then it also, because it's longer, it's going to have more surface area. Any questions? So that was the dispersion force. The next one is a dipole force. Dipole forces exist in all molecules that are polar. So if you're thinking about atoms, they don't have dipole forces. They just have the dispersion forces. Dipole forces happen in polar molecules. These are stronger than the dispersion forces because polar molecules have permanent dipoles. The attractions and the dispersion forces come and go. You get a lopsided atom, and it attracts the electrons in another one, and it causes that one to be lopsided, and you've got this little bit of attraction, and then the first one gets unlopsided, and the attraction goes away. It's very small, but since it happens so frequently, it can be significant. In polar molecules, we always have a dipole. So here we're looking at a compound, and I'm not pointing up there. So this is a polar molecule. The oxygen end here has a permanent partial negative charge, and the hydrogen end has a permanent partial positive charge. It's small. It's not like a +1, -1. These are not ions, but it's just a little bit of an imbalance, but it's always there. And so we'll have always this attraction between the negative end of one and the positive end of the other. So those are space-filling models, and here are electrostatic potential maps. Looking at the electron distribution, we see that there's an increase of electron density around the oxygen. That is attracted to the decreased electron density over here because this is a little bit more positive. So this is attractions, again, between opposite charges. But now those charges are always there. Any questions? So polar molecules have dipole forces in addition to dispersion forces. Everything has dispersion forces. Polar molecules also have dipole forces. So if we look at these two compounds, formaldehyde and ethane, their molar masses are almost identical. So if we're looking at dispersion forces, which vary with size, these are the same size. So the dispersion forces between these two are comparable. This is a polar molecule. This is a nonpolar molecule. How would we know that? Well, this is a double bond with an oxygen. And if we look at this carbon and think about my shortcut rules, are there any lone pairs on the central atom? No. Are all the atoms bonded to the central atom the same? So the first condition is met, that there's no lone pairs. But the second condition, that all of them are the same or have the same electronegativity, is not met. This is a polar molecule. This one, you might have a little more trouble identifying as nonpolar. A carbon-carbon bond is going to be nonpolar, obviously. Carbon-hydrogen, though, they are a little bit different in electronegativity, but I told you that's the one bond that I want you to remember is nonpolar, even though it's different atoms. Carbon and hydrogen are similar enough in electronegativity that these bonds are nonpolar. So anytime you just have carbons and hydrogens, it's a nonpolar molecule, no matter how it's arranged. So this one's nonpolar. We look at the boiling point and the melting point. The polar molecule has a much higher boiling point, minus 19, I mean it's still low, but minus 19 degrees Celsius. The nonpolar is minus 88 degrees Celsius. And we also see a difference in their melting points. So what are we looking at here? Here we're looking at dipole moment, which is measured in dBs, and boiling point measured in Kelvin. So here we've got propane, dimethyl ether, ethylene oxide, acetaldehyde, and acetonitrile. We see that these guys all have similar molar masses, right? Not exactly the same, but they're comparable. That tells me that the dispersion forces are similar in these. So why does this have a higher boiling point? Because it's more polar. We haven't talked about measuring the dipole moments. We haven't done calculations with that, but it can be measured. In measuring the dipole moment, this one has a higher dipole moment than this one. We see that as the dipole moment increases, the boiling point increases because the molecules are more attracted to each other. So intermolecular forces have a big impact on melting and boiling points. They also affect mixing of things. So polarity is important in determining miscibility. So this is a funny word that doesn't come up in everyday life. Miscibility. You need to know what that word means. Miscibility sounds a lot like mixability, which is not a word, but mixability, if I say that, you know what that means, right? Ability to mix. Miscibility means mixability. Means the ability to mix without separating. And we use it in terms of liquids. What? Like oil and water are not miscible. Alcohol and water are miscible. You can put a little bit of alcohol in water, they'll mix up just fine. You can put a little water in the alcohol, it'll mix up just fine. So they're completely mixable. Here we have pentane and water. Water is a polar molecule. Pentane, being just carbons and hydrogens, is nonpolar. They do not mix together, just like water and oil do not mix together. So we say that these two are immiscible. They do not mix. So the little phrase that we use is like dissolves like. Of course there are exceptions, but in general, if you have two polar substances, they'll mix together pretty well. If you have two nonpolar substances, they'll mix together pretty well. But if you try to mix a polar and a nonpolar, they're not going to mix very well. Okay? So we should be able to do things like this. Identify which of these molecules have dipole-dipole forces. So what sorts of things have dipole-dipole forces? Polar molecules. So we need to identify which of these are polar. So this is Ci4, and I put the name out here because sometimes that gets misinterpreted as Cl4, but why would 4 chlorine atoms bond together? Well, Ci4, so you're going to have 4 iodines attached to the carbon. And if you go ahead and count all the valence electrons and everything, you're going to have octets around each of the iodines. I'm not going to do all of them. Are you going to end up with any lone pairs on the carbon? No. Carbon likes to form 4 bonds. And have we ever seen carbon with lone pairs? No, we don't see that in this class. So carbon's going to make 4 bonds. So we look at the carbon, we say, are there any lone pairs? No. First condition met. Are all the atoms bonded to that central atom the same? Yes. So both conditions are true. This is a nonpolar molecule. So being nonpolar, does it have dipole-dipole forces? No. Nonpolar, so no. No dipole-dipole forces. How about CH3Cl? So that's in carbon in the middle. Now we're going to have a chlorine over here, and a hydrogen, and a hydrogen, and a hydrogen. And that chlorine is going to end up with lone pairs. Again, the carbon's going to make the 4 bonds. It's going to have the 3 hydrogens and the chlorine. Is this a polar molecule? It is. It doesn't have any lone pairs. So this is symmetrical around the carbon in terms of how those electron groups are arranged. But chlorine has a very different electronegativity than these hydrogens do. Okay? So this is a polar molecule. It's lopsided. It's not symmetrical. This is a polar molecule, so does it have dipole-dipole forces? Yes, it does. How about HCl? Diatomic molecules are actually pretty easy. If the 2 atoms in there are different, most likely the bond is polar and the whole molecule is polar. So hydrogen and chlorine are different, right? So I expect you to assume that that's a polar bond, polar molecule. So that's a polar molecule, and therefore, yes, it has dipole-dipole forces. If we have something like N2, that's also 2 atoms, 2 nitrogen atoms. Is the bond between 2 nitrogen atoms polar or nonpolar? Nonpolar. A nitrogen atom and a nitrogen atom both have the same electronegativity, right? So that's going to be a nonpolar molecule, and it will not have dipole-dipole forces. Any questions? Next type of intermolecular force is called hydrogen bonding. Hydrogen bonding is kind of a misleading name because it makes you think that there's bonding, like chemical bonds, between hydrogens. And that's not at all what it means. It's really a sort of super dipole-dipole force. So hydrogen bond is super dipole-dipole force, extra strong. So what we've got going on here is we've got a hydrogen atom. In order for a substance to have hydrogen bonding, it has to have hydrogens. The hydrogen must be bonded to a fluorine, an oxygen, or a nitrogen. And the reason that these are the ones that are involved in hydrogen bonding is that they are very small and they are the most electronegative atoms. So hydrogen bonding is stronger because the partial charges involved here are larger than in just regular polar molecules. And the size of the atoms matters because those small atoms, fluorine, oxygen, and nitrogen being small, can approach each other very closely. So being able to get close, we've got shorter distance, that increases the attraction. Having these partial charges being larger also increases the attraction. Okay, so how do you remember this? So we've got fluorine, oxygen, or nitrogen that are bonded directly to a hydrogen. That's what we have to have in order for hydrogen bonding. Do you remember the movie E.T.? I was a kid when that came out and saw it in the theater. It was like awesome. So what was E.T. always saying? Phone home. And he point, phone home, E.T., phone home. Phone home. Phone home. Do you see it? It's not spelled right. E.T. didn't know how to spell. F-O-N, one of those bonded to hydrogen. That's what you need for hydrogen bonding. So let's look at hydrogen bonding in ethanol and in water. I'm going to look at the water first. So here we have structural formulas for water. We know that it's bent because we've studied that. It's got lone pairs on the oxygen, and so it's got this bent structure. The oxygen is more electronegative than the hydrogen, and so we end up with this partial negative charge and a partial positive charge. This is a polar molecule. In water, we have hydrogen bonded to oxygen. So phone home, it's the O in phone bonded to hydrogen. Because these bonds exist, we can have hydrogen bonding. The hydrogen bonding is not between the hydrogen and the oxygen on the same molecule. It's between the hydrogen on one molecule and the oxygen on a neighboring molecule. It's an intermolecular force. It's between molecules. This is an electrostatic attraction. This partial positive charge is relatively strong compared to a molecule that doesn't have fluorine, oxygen, or nitrogen, because oxygen is very electronegative. The partial negative charge here is extra strong because oxygen is so electronegative. And because it's also a small atom, these molecules can come very close together. So the hydrogen bond is the electrostatic attraction between the hydrogen on one molecule and the oxygen on a neighboring molecule. Okay with that? Here we have ethanol. In ethanol, we have hydrogen bonded to oxygen. We have a polar molecule. Those are the situations we need for hydrogen bonding. So the hydrogen bonding occurs between the hydrogen on one molecule and the oxygen on a neighboring molecule. If we look at electrostatic potential maps, the blue is a more positive charge and the red is a more negative charge. And so it's this attraction between the positive and the negative charges, but between molecules. So again, hydrogen bonds are between molecules. There's a reason I'm emphasizing that. People get messed up.
Well, what do they get mixed up with?
Well, they get confused and think that the hydrogen bond is this hydrogen to this oxygen. That is a bond between hydrogen and oxygen, but that's a covalent bond. That's a sharing of electrons, an overlap of orbitals. That's not what hydrogen bonding is. Hydrogen bonding is a form of a dipole-dipole force, which is attractions between partial charges on adjacent molecules.
So they have to be polar?
Have to be polar. Mm-hmm. But if you've got fluorine, oxygen, or nitrogen bonded to hydrogen, you're going to have a polar molecule. Because fluorine, oxygen, and nitrogen almost always have lone pairs. And the lone pairs is what makes it polar, because it gets, asymmetrical. So chemical bonds, again, are between atoms inside of a molecule. Those are the strong bonds. Hydrogen bonds are only 2 to 5% as strong as a covalent bond. So like 1/20th as strong at most. Okay? They're much weaker. We see that compounds with hydrogen bonds have higher melting and boiling points than polar molecules of the same mass that do not have hydrogen bonding. So if we compare ethanol and dimethyl ether. So ethanol has an oxygen-hydrogen bond, and it's a polar molecule that's going to have hydrogen bonding. Dimethyl ether has hydrogens and oxygens, but the hydrogen isn't bonded directly to the oxygen. This one may be a little hard to see in the space-filling model, but what we've got going on there is this. The reason this is polar is because there's lone pairs on the oxygen. Is there a hydrogen-oxygen bond within that molecule? No. It's got hydrogen, it's got oxygen, but they're not bonded to each other. This is a polar molecule, but no hydrogen bonding. Same molar masses, and look at the boiling point. So ethanol boils at positive 78 degrees Celsius. Dimethyl ether boils at negative 22 degrees Celsius. That's a huge difference. The difference between these two really is just the presence of hydrogen bonding. Hydrogen bonding holds the ethanol molecules more tightly together, and so in order for it to boil, you have to give it much higher thermal energy. Any questions?
The structure for the hydrogen bond will like it's always gonna look at the top one. It'll show like OH and F or OH and N. I mean,
Yeah, you have to have fluorine bonded to hydrogen, or oxygen directly bonded to hydrogen, or nitrogen directly bonded to hydrogen.
and it will always show up like that. Like the top one. As it works to the right.
Yeah, well, you have to look at, yeah, so here we see OH. Here there's no OH. And especially on a test, I'm going to try to be very clear and not confusing about where the bonds are. Because I know you look at something like this and you're like, I'm not sure what that means, right? Well, this means carbon with 3 hydrogens on it is bonded to the oxygen, and that oxygen's bonded to another carbon with 3 hydrogens on it. So that's kind of getting into OChem. But this we call CH3, and this is carbon with 3 hydrogens on it. And then in the middle, we've got oxygen. So if we compare different hydrides, so these are group 6A. No, they're not. Who proofreads this book? What group is oxygen in? 6. What group is carbon in? 4. This is group 6A. This is group 4A. So if we look at group 4A atoms, carbon, silicon, germanium, and tin, they're all going to form similar compounds with 4 hydrogens. And we see that their boiling points, the boiling point of CH4 is the lowest. And as we increase in molar mass, we have a general trend that the boiling point increases. These are going to be nonpolar molecules, and so this increase in boiling point is due to the size of the molecule increasing. A larger molecule is going to be more polarizable, and so the dispersion forces will be stronger. For group 6A, we've got oxygen, sulfur, selenium, and tellurium. And these are all polar molecules, so we see that overall the boiling points are higher than for the nonpolar molecules. But the other interesting thing we see, we have this trend, again, because as you increase the molar mass, the dispersion forces get stronger. But who's bucking the trend here? Water. If we're just looking at the trend, we would expect water to be, oh, I don't know, somewhere down here, right? Around minus 100 degrees Celsius. But its boiling point is way up here. All of these are polar molecules, but only water has hydrogen bonding. Dihydrogen sulfide is a polar molecule, but it doesn't have fluorine, oxygen, or nitrogen bonded to hydrogen. So this has dipole-dipole forces, but it doesn't have super dipole-dipole forces called hydrogen bonding. So water has an extremely high boiling point for its molecular size. It's really crazy, actually. What would happen if water boiled at minus 90 degrees Celsius? All of the water on the earth would boil and go into the gas state. Do you know that your body, I don't know what percentage it is, but your body contains a high percentage of water? That wouldn't work out very well, would it? Where would the fish live? There'd be no rain. Just, nothing would work out very well. So we should be able to answer questions like this. Which has a higher boiling point? Here they're asking about HF or HCl, and then the dreaded question, why? Well, let's look at these. So we've got HF and we've got HCl. Those are 2 diatomic molecules, right? So we don't have to think about lone pairs around the central atom or anything. We just have to identify, is this a polar bond? Yeah. So this is polar. Is HCl a polar bond? Yeah, so they're both polar. So let's list the types of forces that these have. Do they have dispersion forces? Yeah, everything has dispersion forces. So they both have dispersion forces. And I'll just put a check mark there. That has dispersion forces. Do they have dipole-dipole forces? Yeah, because they're both polar. So they got dipole-dipole forces. Do they both have hydrogen bonding? ET, phone home. Fluorine, oxygen, or nitrogen bonded to hydrogen. Is there fluorine, oxygen, or nitrogen in HCl? No. Is there in HF? Yeah. In fact, that's all there is that HF bond. So this has hydrogen bonding. And this has no hydrogen bonding. So comparing boiling points or melting points, the first thing to look at is what types of forces are present. So here we've got a difference. HF has hydrogen bonding, HCl does not. This is the strongest intermolecular force. So this one's going to have a stronger attraction between molecules than this one. So which one is going to have a higher boiling point? The HF. So this one's got a higher boiling point because stronger intermolecular forces, we abbreviate intermolecular as IM. Stronger intermolecular forces gives us higher boiling points and melting points. This is going to have a lower boiling point because it's just got dispersion and dipole-dipole forces. If all of, I can't do 2 pointers at the same time, if all the kinds of forces are the same, then you're going to look at things like molar mass. Is one significantly heavier than the other? That's probably going to have the stronger forces. Or you're going to look at the shape of the molecule if they're both the same size. Any questions? There's one more force. This has only shown up in textbooks as an intermolecular force in the last few years. Not that it didn't exist before, but I don't really like it in here, but it's in here. An ion dipole force. So the thing about the other intermolecular forces is they can happen in a pure substance. So water, just water molecules, you've got hydrogen bonding occurring between them. In an ion dipole force, this cannot happen in a single pure substance. It can only happen in a mixture of 2 substances at least. So ion dipole is an attraction between an actual ion and a dipole in a polar molecule. So this happens when you've got ionic compounds mixed with polar compounds. This is really important because this is how water dissolves lots of different ionic things, but in my book it's not technically an intermolecular force. So what's going on here? So water has a dipole, and sodium chloride has 2 ions. The chloride is attracted to the positive end of the dipole in the water. The sodium ion is attracted to the negative end of the dipole on the water molecule. And by surrounding the chloride with water molecules and surrounding the sodium ion with water molecules just facing the other direction, we can coax the sodium and the chloride ions apart from each other. And so this force is between a dipole and an ion, the ion dipole force. This is stronger than a hydrogen bond because we actually have a full charge here. Even a hydrogen bond is not a +1, -1 charge thing. It's still a partial charge. Here we've got a full -1 charge. Here we have a full +1 charge. Q1 times Q2. The force of attraction is going to be greater. Any questions? So here's a summary of these types of intermolecular forces. They are all attractions between positive and negative charges. The difference is how those attractions come about. Dispersion forces present in everything. We've got instantaneous dipoles, just temporary, random polarness of atoms or molecules. Dipole present in all polar molecules. You have to have permanent dipoles. So because the dipoles are always there, it's going to be stronger. Hydrogen bonding, again, we've got ET phone home, FON or 8, or FO or N directly bonded to H. These are stronger than dipole forces because these bonds are more polar than the regular polar bonds. And then the ion dipole forces are even stronger because now we have a full positive or even +2 or +3 charge and with the partial charge. So you need to know the order of the strength. You do not need to know these actual numbers, but just that going from lowest to highest, dispersion, dipole, hydrogen bonding, and ion dipole. Any questions?
Will the iron dipole be on there?
The ion dipole will be on the test, yes, even though I don't like to call it an intermolecular force. See, intermolecular means between molecules. So is an ion a molecule? I don't think an ion's a molecule. Of course, you could argue that about the atoms up here, too, but whatever. Hydrogen bonding is important in lots and lots of different things. One of the things it's important in is your DNA. So I know some of you have taken biology and are very interested in that sort of thing. Your DNA consists of 2 intertwined strands. It's got a sugar phosphate backbone with these little base units attached to that backbone. And there are 4 different bases: thymine, adenine, cytosine, and guanine. And we usually abbreviate those as C, A, T, and G. Thymine and adenine both have the potential for hydrogen bonding. So here we've got a hydrogen-nitrogen bond, and here we've got a hydrogen-nitrogen bond. And so we can get hydrogen bonding between the hydrogen on the adenine and this oxygen on the thymine, and between this hydrogen on a nitrogen and that hydrogen and that nitrogen. So thymine and adenine can form 2 hydrogen bonds. So they pair up, they match up very nicely. Cytosine and guanine are capable of making 3 hydrogen bonds together. And so they pair up very nicely. So C and G always pair together. A and T always pair together. As your body replicates your DNA, it unwinds the strand of DNA and uses that as a template to make a new one. And as the new one forms, A and T match up, and G and C match up, and the same things happens on the other strand. And because they hook together like specialized magnets or like a lock and key sort of, you end up with 2 identical strands of DNA. And the reason it can do that is because of hydrogen bonding. Question?
So could you break those hydrogen bonds and put whatever you want?
You can break the hydrogen bonds.
And if, let's say you find something that would substitute saline or stimuli or something with that, could you place that in there?
Yes, in theory, you could have some other molecule here that would hydrogen bond with the adenine and take the place of the thymine.
Would
In
that change
theory,
something?
that would probably change something, yeah. It probably would. Biochemistry, I think, is, I'm not a big fan of biology. Somebody needs to study biology, so don't be offended. My thing is chemistry, but I do like biochemistry. And this is biochemistry. It's looking at the chemistry that's occurring in living things, right? And so one of the things about biological molecules, they tend to be really big. DNA is huge. You can actually, if you unwind it, you can actually see it. It's so large, it's visible. If you heat this DNA, heating it will break those bonds, those hydrogen bonds. And proteins are also held in a particular conformation by hydrogen bonds. And so when you heat them, the hydrogen bonds break and you mess up the structure. We call it denaturing. That's one of the things that happens when you cook an egg, right? An egg has a lot of protein in it, right? That's why some people eat eggs. So you put the egg in the frying pan, right? My boys playing football, and they're all about, we got to get more protein. But you put that protein-rich egg in a frying pan, and you heat it up, and what happens to it? Well, you may lose some nutrients, but just visually, what do you see happening? It gets more solid, right? The white part, which was really kind of clear and nasty looking, gets opaque and more solid, and the yolk that was runny and bright orange becomes firm, right? And the color changes a little bit. So what's happening there is by heating the egg, you're denaturing the proteins and you're causing them to have different shapes. And that's one of the things, do you remember the safety video where he put the egg into some, I think it was sulfuric acid? Well, things like sulfuric acid also denature proteins. You've got a lot of protein in your body, like in your eyeballs. And so you put acid in your eyeballs, it messes up the proteins, and you don't get those back. You can't undenature them. So
if you have a really high fever, will that mess with you?
That's a good question. If you had a really high fever, would that mess with you? So a fever that your body does to itself will never go high enough to actually cause damage. If your temperature being elevated is due to external heat sources like sunstroke, or being in a hot room, heat stroke, then your body temperature can go too high, and yeah, that's going to wreak havoc. But your body doesn't really go much above 106 on its own.
Will it break the bonds?
It can break bonds, yeah. And so I got up this morning, and you can't tell, but I actually used a curling iron on my hair. How does a curling iron or a flat iron change how your hair looks? The heat changes, it breaks some of the intermolecular forces that are holding the proteins in your hair the way that they were. Curly hair, the proteins are different than in straight hair. And when you heat it and then let it cool in that new position, you can change how those proteins are aligned with each other. This comes into all sorts of things.